Good afternoon, everyone, and welcome to today's webinar on From Strain to Report, using strain gauges to do experimental stress analysis. Your microphones will stay muted throughout the presentation in order to avoid feedback. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. However, you are welcome to type in your question at any time. Our presenter today is Jens Borsch. Jens has 12 years of product management experience. During that time, he has held either direct responsibilities or served as a team leader for nearly all of the products in the test and measurement world of HBM. That includes strain gauges, amplifier systems, and DAC software. Jens is based in Darmstadt, Germany. Jens, it's all yours.
Yeah, so thank you, Krista, for this introduction. Good afternoon, everybody, and welcome to this webinar. The next 30 minutes, I want to speak about how to, I want to speak about using strain gauges to do experimental stress analysis. Okay, what I want to do in detail. First of all, I want to start with some theory behind what means strain, what means stress, and what we understand about either. What is it? And how to get from strain to lifetime, and that it will not get too boring. I want to give you some practical examples. Yeah, just some pictures about ESA. After that, I want to come to the main topic, that is an explanation from building up a measurement chain. That means from the right strain gauge, how to find the right strain gauge, how to apply the gauge, how to connect parameters to choose the right amplifiers, and last but not least about the software. Krista already mentioned at the end we will have some, you will have the possibility to ask questions, and before that I will give you some additional information. That means links to other pages where you can find more information. Okay, that means we start now with this definition part. And the first question is, what means stress? Stress is the measure of internal forces or internal pressure in a component. Yeah, let's say you have a metal bar. Yeah, and as you can see here, if you put forces here and here on the bar will get longer and thinner. Yeah, of course, it does not look like that in the reality in case of steel. Yeah, but it gets a little bit longer. Yeah, this is shown much more than it is in reality. Okay, that means you see internal forces in here. Yeah. And if you increase always the external force, yeah, on both sides, yeah, then it first it will start to deform, and then it will come to a limit where it will not go back to this original size. Yeah. And after that, quite even worse, it will break. Yeah. So that is stress. And stress is always a local property. So not on all points of these metal bar we have the same stress. So it depends on the location. So what we understand under ESA. ESA means experimental stress analysis, and that is to measure the stresses in the material. Yeah? And what is the aim of that? To predict the lifetime and to guarantee that it will not break, that it will survive the lifetime it has to survive. Yeah? We don't look for a huge impact here. Yeah? We do not go to the limit. We have the normal lifetime of a component. That is either simulated or then really tested in a test bench or on a test track, and then we check if it will survive. It is always an optimization process. Yeah, of course, you can make your component quite big, quite heavy, that it will withstand everything, but then you use too much material, it gets too heavy. Yeah, we have to save energy, we have to save material because it is cost. So we always have to make an optimization process. And this is part of either experimental stress analysis. Okay, how to get from strain to lifetime. We measure the strain. Yeah, we will do that later on with the strain gauge. But the first question, what means strain? Yeah. Strain is the extension, or the opposite, the contraction of a material. Yeah. On the picture before, if you put 4 external forces on the left and right side, then the material will get longer or shorter. Yeah. You see here the point 1 and 2. If you put external forces here and here, the material will get longer. Yeah. That means strain, and that you can measure. Stress, as I mentioned before, these are the internal forces. There's an easy connection between strain and stress. This is defined by the Young's modulus. Yeah, and that is a material-depending figure. Yeah. So there's an easy calculation. You just take the strain, multiply it with the Young's modulus, and then you have the stress. Yeah. And maybe you remember here that's a Hooke's law, and we always are in this area, because here you are in the area where when you release the forces, it goes back to the original position. Yeah. In this area on the right side, it doesn't go back. Yeah, and at the end it will break. So we always are here in that area. Okay. And in that area, the Hooke's law is valid. That means we measure strain, we calculate the stress, and then we sum up all the stresses we have measured. Yeah? Let's say we have a component, let's say in the car, and then we have a typical load profile. We put that load profile on the component, and then we sum up all the stresses, the cycles. Yeah? You always have cycles there. We sum up all these cycles. You can describe a cycle by its range. Yeah, that is the size of the sinus curve and the medium value. Yeah, the medium value can be seen as an offset. And when you count cycles, yeah, you count so many small cycles, so many big cycles. These can be shown in a so-called rainflow matrix. So rainflow matrix is it's a small data file, but it contains a lot of information. It contains information how much stress the component has seen during this load profile. Yeah, this here is a rainflow matrix. So that's the first step. The second step is putting that summarization of the stresses into the Wöhler curve. The Wöhler curve, is also known as SN curve, describes when a material breaks. So how many cycles a material can withstand, depending on the level of the strain. Of the stress, of the stress level. For example, on that stress level, here on that level, it can withstand so many cycles. On a lower stress level, it can withstand much more cycles. Yeah? So this Wöhler curve comes from an experiment. Yeah? You have to do a lot of experiments to get such a curve from your material. And probably you can imagine if you take that rainflow matrix into that Wöhler curve, you will get an estimation. Will it withstand that load profile, yes or no? Or how many times it will withstand this load profile. Then imagine, let's say the load profile we have simulated means 10,000 miles, and we get out from it will withstand it 20 times, then it means we can go with the car 200,000 miles, and then it will break. of course with a probability. So we measure the strain, we calculate the stress, we sum it up in a rainflow matrix, and then together with a Euler curve we can estimate the lifetime. That's the flow of data, how it works. Good. Some practical examples. Where in the world we speak about ESA and where strain is measured, stress calculated, and so on. I think I have here some nice examples. Let's start with some examples from the transport area. Here on a helicopter, the blades of a helicopter, or the wings of a plane. I think that's the Airbus 340. Here satellite. Here on a railway track. You can see here the strain gauges, or on the railway itself, here on the bogie. Here this nice fast sailboat, the catamaran. By the way, that is the world's fastest catamaran. It runs at the moment in South France. Or for energy, here a pipeline where you measure the strain, or this wind blade from a wind energy station. Yeah. In that case, it is a static measurement. I have been on the customer side where they make a dynamic measurement that looks really impressive when you see dynamic measurement there, because you can feel the energy and you can hear it, and yeah, feel the vibration. That's really impressive. The only thing you always have in mind, please don't break now when I'm beside. Yeah. Good. Or here the construction of that offshore platform, also to generate wind energy. That's quite difficult to measure here, because you can imagine it is under the sea, a lot of salt water, not a nice condition for a strain gauge. But we have a lot of experience here, so we can offer you a solution to apply strain gauges even underwater. Some examples for civil engineering, so much bigger construction like a bridge. Here on a specimen of a cement, a concrete, and this is the monorail, for example, or some old column of some building where we calculate, will it survive or not. Engine building. You see here a really nice picture of a strain gauge rosette. This is the chassis of a car. But also other examples for medicine or sports. Okay, medicine I don't like, especially when we speak about teeth. But here on a mountain bike, there's a component from a bicycle, or here on a sliding bob. So everywhere where you have mechanical components which are under high load, which has to withstand a lot of energy, of a lot of impacts, the ESA is important, because you always, in an optimization process, it must be not heavy, it must be light, not so much material, but it must be withstand all the impacts. It's not allowed to break. So if it breaks, it could cost a lot of money, or even worse, the life of your customer. So it's very important to measure the stresses and to calculate and to validate that it will withstand the typical impact. Okay, I think we have now some ideas what means ESA. Then I want to go to the second topic. We build up the measurement chain. Let's start with the strain gauge. Choose the right one. If you look in the strain gauge catalog of HBM, there are a lot of types, a lot of series, but to make it easy, if we speak about the applications I mentioned before, that means if we are in the world of either, take the Y series. Yeah. There are some exceptions, but 99% you can do with the Y series. Only if you speak really about high temperatures, and high means bigger than 200 degrees Celsius, or weldable strain gauges, or if you measure in a vacuum, but these are really strange and seldom applications. Normally, Y series. Why the Y series? The Y series is flexible, so it does not break so quickly. Yeah, you can bend it, yeah? And it's easy to handle. Yeah, it's a strain gauge on a fully emit carrier with a Constantan grid. Yeah, so quite easy to handle. And we will come back to that later. We have a wide range of geometries. I will explain later on what geometry means what. We have different temperature compensations. Quite important, it is available. That means you can order it directly from stock. It has an encapsulated grid, so it's already protected. And it comes with all the information you need. The gauge factor, the transverse sensitivity, and so on. And last but not least, also available with different resistances. I will come back to that point later. So, normally Y series, if we speak about strain gauges from HBM. Okay, I mentioned different geometries. What are the typical ones and when to take which one? A linear one. Linear means you have one grid. You take that gauge if your main direction of the stress is known, either by an HBM calculation, so you know, okay, there's my main direction of the stress, or it is obvious by the shape of your component. Yeah. So if you know the main direction is in that direction, take a linear gauge. You take a T-rosette. T-rosette means you have two grids, so one grid more, and these grids are 90 degrees to each other, so a T shape. You take that gauge if you have two stresses. So if you speak about a biaxial stress state, you always have one main direction and a second direction, and these are always 90 degrees to each other. And you take that, the T-rosette, when you have a biaxial stress state, but you also know the direction. So similar to the linear gauge, again you know the direction. You take a torsion or shear stress gauge if you have a torsion bar. Yeah? In that case, the two grids, again as a two grid gauge, are 45 plus minus 45 degrees to the axis, main axis. Yeah? You take that if you speak about torsion torque. Yeah? A rosette, three grids. You take that again if you have a biaxial stress state, but with unknown direction. And the aim of that gauge is to get the direction. So the result, by measuring with three channels, all the three grids, and then some calculation by software, then you get the information about your main stress, about your second stress, and the direction of the main stress. So you take a rosette if you don't know about your stress in your components. And the result will be that you have much more knowledge about that. Here, typically two types are available. The grids can be side by side, or if you have more problems with space, you can also stack the grids on the top of each other. Yeah. Good. These four are the typical geometries for either strain gauges. But I also want to mention some special geometries. A parallel one. Again, two grids, but not 90 degrees like a T-rosette, but parallel to each other. You take that typically on a bending beam. Or if you want to build up a full bridge, you can take directly a gauge with 4 grids, and then it's quite easy to build up a full bridge. A chain has 10 to 15 grids quite close to each other, and you take that when you do not have a homogeneous stress in your material. You take that if you have a stress gradient. Yeah. Of course, you could also apply a lot of single strain gauges, linear gauges, but that is much easier, and you get much closer together. So to determine stress gradients, you take these chain. And even more special are gauges to measure residual stress. These are internal stresses, for example, in your metal component, whatever, and these result from the heating up process, so the production process. Then you can have internal stresses, and you can measure that by drilling in a hole, and then the stress releases, and you measure that. So that means that is a destroying test. Yeah. And these drilling machines are quite special, and also the gauges are quite special. This is residual stress. Okay. These are the special gauges. I just want to mention them to make a full picture. So typically, you have the linear gauge, the rosette, T-rosette. These are the typical gauges. Good. Let's say we know a lot about what we expect. We know the direction. So we take a linear gauge. Then the next question will be about the grid length. They are grid length from 0.3 millimeters to quite long, hundreds of millimeters. So from quite small to very big. But which one I should take? So my recommendation, take 3 or 6 millimeter grid length. Yeah. A smaller, when you have problems with space. Yeah. If you don't have enough space to glue a 3 millimeter gauge, you have to take a smaller one. A typical example would be an electrical circuit board. Yeah. These days, the companies measure a lot on these boards, and they always take smaller ones. Or take a bigger one if you have an inhomogeneous material, for example, concrete. Yeah. On metal, it's an homogeneous. You can take 3 or 6, but on concrete, you have to take a much bigger one. It depends a little bit on the stone size of your concrete, which one to take. So we have found the right gauge with the right length. The next question will be the resistance. Typical values are 120 and 350 ohms. There are also some gauges available with 700 or 1000 ohms, but 95% are from that gauges. And typically they share it 50 by 50. Yeah. So when to take the 120 and when to take the 350 ohm, normally there's a customer decision. You say, okay, I always use that one, or I always use that one. For example, because of your amplifier system. Okay, if you have an amplifier system which can do both, yeah, then you have to decide. Typically you take a higher resistance if you want to have a lower current flow. For example, because of self-heating. If you measure on a small plastic component, then it should not heat up itself. Yeah? Then you take a 350 ohm. Or obviously, if it works on battery, yeah, to get the lower current flow, take the higher resistance. The lower one is more robust against insulation resistance and also IMC. Yeah. So this helps a little bit for these decisions. So the next one is the temperature compensation. If you have a temperature change during your measurement, maybe because it's a longer measurement and the temperature will change, then you should ensure that you adapt the strain gauge to the material you apply the strain gauge on. So if you apply the strain gauge here on steel, then you have to take a strain gauge adapted to that. In the HBM world, the code is 1. If you glue on aluminium, take that one, and so on and so on. Why? Because then the strain gauge is adapted to the temperature change of the material, the alpha. Yeah, that one. How much it gets longer because of temperature. Yeah. And these should be equal. Especially, as I mentioned, on long-term measurement where the temperature changes. Typically are steel, aluminium, and composite material. Yeah, these are the 3 typical adaptations. Good. Now we get closer and closer to our amplifier system. So we have to think about how to connect it. There are different possibilities. You can use the integrated solder tabs. That means you can directly solder on the strain gauge. So that's quite convenient. So this is a typical gauge. But you can also have copper leads. Yeah, here. That means you apply additional solder terminals somewhere here, and then you glue that to the solder terminal, and then the cable on that solder terminal. The benefit is that you have a mechanical decoupling between the cable and the strain gauge. It's important when you work on higher strain levels. A mixture of that both. You can also have solder tabs with strain relief. So you can solder directly on here, but you also have a mechanical decoupling. So that's a compromise between that both. Or to make it even more easier for you, you can have pre-wired gauges. So you can order it directly with some meters, up to 15 meters of cable. So that means you don't have to solder on site. You get these strain gauges ready-made. You just apply it, you glue it, and then you directly can connect it. We have some Teflon wire here in between the gauge and the cable. We have some, it's not 5 millimeters, sorry, it's 50 millimeters. We have some Teflon wire. Why Teflon? Because it does not stick. So that's some benefit here. So that's the easiest way. A lot of customers who try that say, okay, I always buy that one. Yes, it is a little bit more expensive, but I save a lot of time. And time is money, so it's really worth to try these pre-wired gauges. Good. So we have chosen the right gauge. Then we have to apply it. The first thing, you have to mark your position, defining where you want to apply the gauge. Please do not scratch into the material. Scratching would lead you to wrong values. And before you glue it, clean it. It must be chemical clean. Roughen it before. Yes, roughen it before and then clean it. So it must be chemical clean. That the bonding really works. Bonding. Typically in the world of either you use a quick-acting and cold-curing adhesive. It must go quick, and you can put your component into the oven, so it must be easy to use. There are typical 2 types of adhesives. It's called Z70. You take that for standard surfaces, metal or composite. That's a one component adhesive, very easy to use. You just make a small dot on your component, then you apply the gauge with your thumb, wait 30 seconds, 45 seconds, and then it's ready. Yeah. The second typically adhesive is a X60. It's a two-component adhesive, and you take that if you have a more absorbent or uneven surface, like concrete, for example. Then you take a X60 adhesive. Then after that you have to protect your gauge, mainly against humidity, but also against some mechanical damage. So it really depends where your gauge is applied and how much time it has to withstand and what happens there. Is there a lot of humidity? Is it on a railway track with a lot of vibrations, dust, and maybe stones are flying around? Yeah? Then of course you have to take a better protection. Here you can put a thin film with a nitride rubber. It's called PU140. That's mainly against humidity. SD250. That's some transparent silicone rubber. It looks a little bit like how you clean your teeth. It looks a little bit like that. Yeah, it's a silicone rubber. That's for mechanical protection, or really AK22 ABM 75. That's is a little bit like chewing gum, and metal foil, aluminium foil. That's really for extreme protection if it goes underwater or something like that. Yeah. So different grades, different ways for protection. Good. Now we have applied our gauge. We have now to connect our amplifier. And there are different ways to connect a gauge to the amplifier. In that case, I always speak about quarter bridges. The easiest way would be to connect it by two wires. But two wires shouldn't be really used, because the resistance of the cable depends completely our signal. Yes, of course, you can make a shunt calibration to measure the influence and then to correct it, but what you can't correct is the dependency of the temperature. Yeah? So you also measure temperature. And the quality and the accuracy get worse, yeah? Especially with longer cables. And you lose also resolution, because the Wheatstone bridge is not balanced because of the additional resistance, and then you have to go to a higher range, and higher range means less resolution. So you should not use two-wire technology when connecting a quarter bridge. Three-wire technology, yes, that is much better. Yeah? So you don't have these bad effects. The theory behind it is quite easy. One wire you put into the positive arm of the Wheatstone bridge, and the second wire you put on the negative. So if you have temperature change or the resistance by itself, it's compensated. Of course, only in case of a symmetric cable. So the error that stays is because of the asymmetric of the cable. Yeah? If you want to compensate everything, so even if you have a not symmetric cable, then you need the four-wire technology. Okay, the four-wire technology, there's a patent from HBM, and here really every cable influence is compensated. That means that provides you a top quality signal. Good. Now we know that we use three- or four-wire technology to connect our amplifier. That means it is time now to speak about amplifier. Good. I don't want to speak about our different systems here. I just want to give you an idea about what questions you should ask yourself to find the right amplifier system for you. And I think if you have answers to that questions that will come up now, then you can go to your sales engineer from HBM, and then you can go through that list, and then he, together with you, he can find the right amplifier system for you. Okay, What are the questions you should have? We should ask you about your inputs. So what quantities you want to measure? What analog quantities, or do you also want to measure digital inputs, like a simple yes or no information, or CAN bus, or whatever? Do you want to measure only one type? Do you only measure strain gauges, or do you want to also measure temperatures, voltages, and so on? And is it fixed, or do you need a universal amplifier so that one amplifier can measure a lot of quantities on all channels? Yeah, that means really it's universal and you are flexible. So you have to ask these questions, then it's much easier to find the right amplifier. The second would be outputs. After inputs, you also have to ask, do I need outputs? Like analog outputs or real-time field buses. Do I need that for my application? The bandwidth. Is it a quasi-static measurement I have, or is it really high speed, high sample rate where I need mega samples of sample rate? Well, this is the question. The degree of protection. Do I work in the lab, so I don't need a high protection, or do I need to put my amplifier system into the mud? Yeah, is it on a agricultural vehicle, or is it under a bridge where you have a lot of rain and humidity or whatever? Yeah, where you need a much higher degree of protection, waterproof and all those stuff. Arrangement. Do I need a centralized system? Maybe I'm in a lab and I need a 19-inch system, or I'm on a bridge where I have kilometers in between. That means I need a decentralized system. Now that's a question. About the amplifier technology, do I need carrier frequency, or is a DC amplifier the best for me? No? A carrier frequency, it means you are more robust against IMC. The production area, for example, or on a railway track. You can't work on a railway track without carrier frequency. Also the resolution, number of bits, is a question. The size. Do I need a 19-inch rack, or do I need a very small one because I have to test something on my skis? And I don't want to have a big bag on my a big package on my back. Data storage. Do I always have a PC, or do I need some local storage? Number of channels. Do I speak about 1, 5, 10, hundreds, thousands of channels? And some specialities like, do I need taps? Do I want to have APM? APM stands for Advanced Plug and Measure. And last but not least, do I need some local intelligence? Yeah? Do I want to program my device to do something? So a lot of questions. If you answer that, your HBM sales engineer can help you to find the right system. Okay, so we have our amplifier. Now the next question will be about the software. I want to distinguish between DAC software, so for data acquisition, and for analysis software. Let's start with the data acquisition. So here you should ask, of course, the first question is, does the software support my amplifier system? First question. Okay. If you stay at HBM, of course, the HBM software supports HBM amplifiers. The next question is the ease of use. I know that is a phrase, but we all have a lot of software in our notebooks. We have smartphones where we have a lot of apps, and you play a little bit with the apps, with your app, and then you say, okay, I delete it, or it was a good choose, and you keep it. You don't want to read any books. At least for me, I want to start it, and I want to be able within 5 minutes that I can operate it. So ease of use is very, very important. Of course, also the functionality, but functionality is always fit for purpose. Yeah. Of course, you also have to think on tomorrow. Yeah. So it must be flexible. There must be always more functionality as you need today, because you always have to think, okay, maybe I need that tomorrow. Fit for future means, so it must be a living software. There must be further development. If the development on software stops, it's dead, because there will be a new Windows or a patch for Windows. So if there's no further development, it's a dead software. And last but not least, also data formats. You have analysis software, and then your software must be able to feed that into your analysis software. Good. The typical tasks is to set up the system, to define measurement parameters like triggers, of course to visualize your data, and to do already in the field some analysis. Not big analysis, but some, let's call it validation. That's an important task of a DAQ software. And it's depending a little bit on your application, but quite often I hear it must be able that I can automate something, some customized task. For example, after each measurement, you want to make an FFT, you want to find the peak, and this peak has to go to Excel. Yeah, just one value. And you don't want to do that 100 times manually. You will be able to program that. So when you press stop measurement, then the value goes to Excel. In the world of HBM, this software has a name. It's called Catman AP. Software to do the next step, last step, to analyze data. So what's the right analysis software? Let's speak about some functionality. What this software has to do. It has to work with the data formats I have. Yeah. And then again, the function. It must have a function library that fits to my purpose. Quite often on analysis software you have different packages. So you decide which package I need, and then you buy that package. It's quite usual. Again, ease of use, that you have an overview about your process, and efficiency. Let's imagine you have always the same measurement, and you have to analyze it by the same way. So you want to make one time a report, one time you define how this analysis should look like, and then you say, okay, software, listen, here are 100 files. I will grab a coffee. When I come back, I want to have 100 reports as PDF on my hard disk. Yeah. Then you start the process. You take a coffee, and when you come back, you want to have 100 PDFs. That means efficiency, yeah? Automated reports. And last but not least, the software must be able to handle bigger data sizes. You know this problem with 2 gigabytes, 32 bits, 64-bit system. So such a software should handle also bigger data sizes. In the world of HBM, this analysis software came from the brand Encode, and the names are there: CliffWorks, Design Life, and Automation. So that have been our measurement chain. Then some additional information. Where to find more information besides that webinar here. Of course, on our website you will get all this information. We have one landing page, I think they call it, the colleagues from the Marcom. It gives you an overview about experimental stress analysis. You can find that under this link. Then the Hoffman book. I call it the Bible. That's really a strain gauge reference. 250 pages, really in-deep knowledge about strain gauges, how to work with strain gauges. And you can download that free of charge, this Bible, below that link. The strain gauge catalog, which gives you an overview about all our strain gauges, can be downloaded here, and a lot of tech notes, white papers, also video, how to apply strain gauges step by step, you can find here under these technical articles. Then, last but not least, some links to videos. The first two are concerning our software Catman AP. That's how to work with strain gauges in Catman and AP, and some more general, the first steps to work with Catman AP. Then some amplifier related link, that is this one, experimental stress analysis with our amplifier system Quantum, and there we have a quite new amplifier system, the so-called MX1615, and you have a video there. Good. That was my last slide. So thank you